read or description would be shorter than what you just heard. I think it's very interesting to see how read-OR works using average Hamiltonian theory. The way I explain read-OR is stepwise. First, just think about having one pi pulse in the middle of a rotor period. That's it. I want to build my case step by step. And so you have half a rotor period of rotation, and you have dipolar coupling going on. The heteronuclear dipolar coupling is what I'm interested in. And then I come in with a 180-degree pulse, and then I do free rotation for another half rotor period. Okay, so here I have a little bit extra notation because I skipped all of that homonuclear decoupling part, but bear with me. So the propagator here is, I'm going to use this notation that Klaus Schmidt, and Spies developed for explaining Wahoo-Ha, where the free precession, where there's no pulse, we use the notation of LZ. Z subscript to indicate, well, I'm listening to the Zeeman interaction or the dipolar coupling in the lab. And then I have a pulse coming out, and that I'm going to indicate by P, a pulse, and this is X direction. And then after that, I have LZ again. Actually, I should be a little bit careful. I need to indicate the direction of doing the propagator. You're supposed to read from the right-hand side to the left. And the reason for doing that is, remember, when you dress your central density operator by these propagators or exponential operators, you go from the nearest to the density operator out. So here, what I'm writing is the bunch of terms in front of the density operator, and therefore the first event, the first half rotor period, is represented by the rightmost LZ, and then you have a pulse. That's the direction, okay? What happens after the row 0, that's U minus 1. So I'm not going to bother writing that. Writing 1 is enough to see the situation. So this is equal to, reading backwards, e to the minus I, and then rotor period, first 0 to half rotor period, I have a dipolar Hamiltonian, HIS. It's time dependent because of my magic angle spinning. Okay. And then I have a pi pulse. So RF Hamiltonian for a pi pulse can be written as e to the minus I, pi, that's the phase. And then it's a IX spin operator for X pulse. And then I have the second half of the rotor period, so all that changes for the dipolar Hamiltonian is the time interval. It's a half rotor period to the rotor period. At this point, it's good to remind ourselves that if you hadn't done the pi pulse and you just waited for the whole rotor period, then magic angle spinning removes dipolar coupling. So mathematically, what that means is this equation must be true. That is e to the minus I, 0 to TR. So pay attention to the integration limits very much. So this is important. HIS of T dt equals 1. So the exponent is essentially 0. And when a propagator is 1, you know nothing happens. Dipolar coupling is averaged by after you have rotated one whole round. Okay, so this is 0. That's all good. Why do I want to emphasize this somewhat trivial point? Because I would like to make a point that the second half of the dipolar evolution, this TR half to TR, in other words, this portion, this part, the phase that's developed under the dipolar Hamiltonian is related to the first half of the dipolar evolution phase in a simple way. Because these are just integrals, and I haven't changed my integration argument, the integrand. All I'm worried about is the integration limits. Something that integrates from half rotor period to TR is the difference between 0 to TR minus the 0 to first half. That's true. So the 0 to TR, the whole rotor period is 0. We just said that. So this should come out to be minus the first half of the dipolar evolution. So the second half of the dipolar evolution, the phase that's accumulated is the opposite sign version of the first half. You see in the literature review articles or whatever, people will sketch the sinusoidal oscillations. They'll show the first half in one sign, the second half in the opposite sign. Well, that's basically what I'm trying to express here. So if you hadn't done the 180-degree pulse, the integration will come out to be 0. The average dipole effect is removed by magic angle spinning. All right, so let me go a little bit further. What am I writing here? Since MAS affects the spatial part of the Hamiltonian, we can write the integral of the Hamiltonian in terms of a dipolar phase. So let me show the phase of the heteronuclear dipolar Hamiltonian, HIS. It's the omega IS, the spatial part, the frequency part, times IZSZ. There's a factor 2. Again, I like to keep that factor 2 very explicit. Magic angle spinning is completely independent of anything you do on the radio frequency pulse side. Magic angle spinning is literally changing the orientation dependence of your dipolar couplings or your molecular orientation. So time dependence comes in at the omega IS part. The spins don't care about the magic angle spinning. But the Hamiltonian, because it's a product of the spatial part and the spin part, Hamiltonian, of course, acquires time dependence due to magic angle spinning. So omega IS of t, since this is an integral over time, it's the omega part that should get integrated. And so I can pull the IZSZ out of the integral because that's time independent, and then lump the rest into this phase. I can write it as phi, and I will represent what happens in the first half, 0 to TR over 2, as phi half Rother period. So that's my notation. All right, so this is this overall propagator due to this half Rother period, pi pulse, half Rother period. Now I have a more explicit notation with an arrow pointing to the left in time. And given the simplification, the first half, the free rotation, will give me minus I phi TR over 2 times 2 IZSZ. And then I have a pi pulse. And then I have the second half, and it's oppositing sign to the first half. So I have a e to the positive I phi. Okay, so I'm ready here to see what happens to my density operator. Rho of TR. So my question is, at the end of that Rother period, what is the density operator? What is the spin state or magnetization? I'm supposed to then do the von Neumann equation, the evolution, and I have a rho 0 here. It's going to be sandwiched by u in the front and u minus 1 at the back. And I'm too lazy to write out the u minus 1. It's very long and laborious, but you know it's the opposite sign version of what I have on the left. All right, so I have all these things copied over. And rho 0, what is rho 0? And let me just consider the initial magnetization as pointing along the x direction. And I have Ix here, and I have, okay, IZSZ. This is the pi pulse, and then this free rotation. Okay, so this gets a little bit messy here. What are these red things? This is a trick that we usually apply when we think about homonuclear decoupling sequences. What I'm doing here is I'm inserting a 1, a unitary operator 1, by taking e to the I pi Ix times e to the minus I pi Ix. I insert that in front of Ix after these 3 terms. And so I still hold the equality. And the reason I want to do that is because I want to engineer a rotation by 180 degrees, pi pulse, around Ix onto this IZSZ dipolar Hamiltonian. And the only way I can do that is to combine with the pi pulse original one, e to the minus I pi Ix, with the opposite signed version here, e to the plus I pi Ix. In this way, I can take these 3 terms and rotate it into something else. Okay, let's see if this all makes sense. I still have the Ix, and I have this e to the minus I pi Ix still remaining, but I have managed to change this term. And because 180-degree rotation around Ix simply turns this minus Iz into a plus Iz, I switch the sign of this exponential operator to positive. That carries over to this point. I kept the original e to the I phi to IZSZ here, unchanged. And this term now is sign converted because of my triple product, causing a rotation on the original term. You see what's happening? I inserted a unitary operator in order to do a rotation on the spin Hamiltonian. This is kind of equivalent to the concept of using pulses, which are RF Hamiltonians, to rotate a local spin interaction. I'm using pulses to rotate the dipolar coupling. And here, fortunately, the rotation is easy. It's 180 degrees. All I do is to change the IZ-SZ sign to be a minus sign. That's all. I'm not changing the Z into XY or anything. Now, but you say, but in order to do this, I have introduced these extra things, but fortunately, I pi Ix doesn't touch the Ix density operator because we're in the same direction. This whole thing commutes. So I still have just Ix. But by doing this manipulation, you see what's happening is I have two of those same sign I phi to IZSZ. So I have accumulated my dipolar phase. I doubled it, e to the I 2 phi to IZSZ Ix. And then afterwards, the other side is exactly the same. So now at this point, I can actually do my normal time oscillation of the density operator. And I hope this is clear that you are now evolving Ix magnetization under the influence of IZSZ with its corresponding phase in the front. And so you're going to have an Ix term, and then the other term is the commutation of Ix with IZSZ. That should look like IYSZ. And the oscillation has the phase of the 2 phi. So this looks all complicated, but really what it says, I can represent in a simple diagram. In one rotor period, 0 to TR, I have a 180-degree pulse. And before the pulse hits you, you might think my dipolar coupling has a certain sign. I would just call that positive sign, IZSZ. The pulse effectively inverts the sign for this part. All right. And so because of that, if I hadn't done, let me just make it clear, if I hadn't done any pulse, you continue, and MAS will average out everything. So the fact that you have a negative sign means you get equivalent to 2 times the half rotor period of free evolution. You get non-zero result. Okay, and that's what you want. You want heteronuclear dipolar coupling to be non-vanishing. You want to bring it back, reintroduce. So this would have given you 0 dipole interaction. This is giving you 2 times this half rotor period of net evolution. Okay, so with Redor, what I want to do is to keep accumulating this effect of plus minus in the first half and second half, because this means I have dipolar coupling. All of that complicated exponential operators algebra is doing this. Okay, so then I say that all looks very good, and would like to do this for more rotor periods, because one rotor period usually is too short for me to see any sizable effect, because the typical dipolar couplings for any meaningful distances are pretty weak, and you need to go out long enough. So simple-mindedly, we say, let's repeat what I did in one rotor period by a second rotor period, and I'm getting a pi pulse in a second rotor period. Let's see if that works. Then I get even stronger effect of dipolar evolution and accumulated dipolar phase. And you will find out that this actually won't work. And I can say, okay, why? Why does it not work? Let's say I want to calculate rho density operator at end of 2 rotor periods, starting from the first rotor period result that I just did, which looks like here, right? Then I already know what's the second rotor period average Hamiltonian, because it looks just like the first rotor period. So I have e to the I 2 times phi IZSC, and then there's a pi pulse effect. But anyways, and rho TR, and then you do this. Okay, so this math is some work to go through, but it's not too bad. And so, okay, I have now, and I'm also deciding to change the phase of the pulse for the second one. I said, let me do Y pulse, and it's actually a good idea. In Redor, you do a phase increment of XY. So let's just use Y pulse and see what happens. Okay, so the Y pulse, which is represented by e to the I pi IY, will rotate the IX, and it's a pi pulse, so it just turns IX into minus IX. And it actually is not going to touch the IYSZ, because the IY pulse won't affect IY magnetization. So this remains as minus 2 IYSZ. So, okay, you have a sign inversion here. Otherwise, not a big deal. So then you need to deal with how the central 2 terms will be rotated by the average Hamiltonian for the second rotor period. So again, it's IZSZ here. How does IZSZ impact IX? You have IX, and then it's going to develop into a second term. That will be IYSZ. The original IYSZ will acquire a cosine term, but then it's also going to evolve under the influence of IZSZ into something like IX. I think I'll leave this part to you to prove to yourself, to your satisfaction. The important thing is to pay attention to the sign. The sign is very important here. The minus IX cosine 2 phi. Why do I have cosine squared? Because I have an original cosine 2 phi from the first Rother period. And then I have to evolve a second Rother period. And I have to do cosine 2 phi again. So it's cosine squared, and it gets the minus sign. And the other IX comes out of IYSZ, the invisible term from the first Rother period, evolving in a second Rother period to do another commutation. And IYSZ commutating with IZSZ will give you IX coming out. Maybe I should write that part. So the first Rother period gives me two terms. This gets a cosine, this gets a sine. And by doing the second Rother period, you have to do this oscillation of time dependence again. I need to do cosine. Okay, the phase is 2 phi. Do that again for 2 phi. And then this one commutating with IZSZ will give me IYSZ. You collect the first 2 phi, and then you develop a second sine part. So this is, I'm always applying the solution to the von Neumann equation again and again and again. Okay. So the underlying thing, for just to remind you, it's going to look like this. And I don't swear by the sign. That's too much work to track, and you have to keep track of the sign. Right, so it's always this thing. And here, well, I'm still having to worry about the commutation, but the first term, the cosine term, is always clear because that you don't change the spin operator, but you have to tag along the first Rother period's modulation. Right, so because I'm keeping the same term, that's cosine. All right, but now I need to have the sine term. You know you're going to get this, but the stuff in front, that comes from working out. Okay, normally we write H first, so H comes first. So this is one of these things I glossed over. If you haven't done product operator, hopefully you have done some. When you see the same, you lift it out of the thing, you get square, and then you just deal with this. And when it's square, it's very nice. It's 1/4. And then you get this, and that's just going to give you minus IX. Of course, I don't swear by the sign because I'm just telling you the real thing. You have to work out the sign. Now, sign is important. If you don't get it right, you are going to not get the right answer. So, but the terms that's important is you're going to get something like IX. Okay, and then now this is nice. This is sine square, 2 phi. This is cosine square, 2 phi. And you know, if they have the same sign, cosine square plus sine square would be 1. And that actually is the case, that you do have the same sign. They both get minus. So you get minus IX. And then these cross terms cancel. So by the end of 2 Rother periods, you've got the opposite sign term that's the same as the initial density operator. There's no dipolar coupling. This is no good. It's not useful. Okay. All right, so you haven't recoupled. If you do this 1 pi pulse per Rother period, it doesn't work. There's no recoupling. And so now I want to use my simple-minded plus minus sign without going through any of these math to illustrate the idea. And I think this is, in practice in the lab, this is what you want to be able to do. Dipolar coupling without hitting the pulse is its natural sign, it's plus. Hitting a pulse, the pulse turns it, 180 degree, turns it into minus sign. At this point, it goes on. There's no pulse. It keeps its minus. And the pulse hits it again, it switches to plus. Now, why does this prove that this is no net dipolar recoupling? It's because the first half of the Rother period, where things are synchronized, one Rother period, it gets the positive sign, the next Rother period gets negative sign. They cancel. In a second half Rother period, where things are synchronized. Minus sign here, plus sign here, no good. You cancel. So with magic angle spinning, the important thing is to always remember that the Hamiltonian is time dependent because of rotation. All your molecules are changing their angles relative to the B0 field and so on. So the Hamiltonian has to be considered in the time very much which part of your rotor period you're at. And then you need to think in that way. So read-or like this doesn't work. So now if you can guess what's going to happen next. If you flip, you add another pi pulse, right? If you do that, then things are good because the pi pulse, it's going to flip the dipolar coupling sign, Hamiltonian, and then it's this. And why is this good? Because the first half of the rotor period, it's both positive, it's cumulative. Second half, both negative, cumulative. And now, unlike scalar interactions like J coupling, where if you have equal time of plus and minus, you say everything averages. In MAS, under magic angle spinning, that doesn't average because the second half is effectively the same as the first half. So is that clear? So if you keep having plus minus by having 2 pi pulses per rotor period, and then you continue, you must have this place to write this. Keep going with a few plus minus. So this is what you want. So that's what read-or does. When people sketch these sinusoidal waves and then they say, I'm flipping the sign and so on. So it's basically this idea, okay? In order to accumulate the net effect of the dipolar recoupling that you had for one rotor period, you must introduce another pi pulse at the end of the rotor period. And so by doing that, you can go through the math that things will work out. Before the pi pulse, you got something like this, which we showed earlier. Right after the second pi pulse, you have managed to change one of these signs, and that's a critical change. You need that, minus IX, and then you can go through the same calculation, but you now pay attention to the signs. So instead of having a IX cosine square plus sine square thing, you get cosine square minus sine square. And that's all the difference. Cosine square minus sine square is, if you remember one of these trigonometric terms, it's cosine. One of these half angle, double angle relations, and it's cosine 4 phi. That phi is the dipolar phase accumulated under the recoupling, and you want that phase to keep accumulating. 4 phi, 8 phi, as you increase mixing time or increase the number of rotor periods. So this demonstrates with 2 rotor periods, you collect 4 phi. Each phi is defined as half rotor period net dipolar phase. Okay, so that's this. All right, so there's a little bit more to talk about. You say, oh, this is all very good. Read-or is basically a train of pi pulses that come out spaced every half rotor period. That's great. You can do this. You have I channels, S channel, and maybe I put all my pulses on the S channel, but then it won't work because if this is happening on my nitrogen channel and carbon is just nothing, well, by the time you want to detect the carbon chemical shift would have run away from me. Chemical shift interaction, precessing, all of that stuff. So you want to have a pure dipolar coupling effect. So this is where you have to say, well, okay, I need a Hahn echo on the observed channel, and Hahn echo means I have to put a pi pulse in the middle of the entire read-or mixing time. So what you want to do is then 0, 1, 2, 3, 4 rotor periods. This is my background channel, and the other channel, I'm waiting before I detect. So let's put the central pulse right here because I need that for refocusing the chemical shift interaction. And you say, why does read-or still work? Well, read-or doesn't really, bilinear heteronuclear dipolar coupling doesn't care whether the pulse happens on the I side or S side. As long as you keep 2 pi pulses per rotor period, all you do is introduce an inversion, right? So by putting 1 pulse up there, it works. Or you can decide, I'm going to alternate 1 pulse here, 1 pulse here, 1 pulse here. You can do that too. So because it's always a pi pulse, whether that pi pulse happens in the pi ix side or e to the minus I pi sx, you know what's going to happen, that izsz is always going to just turn into minus izs. So it actually doesn't matter where you put the pulses, but for the purpose of removing chemical shift evolution, the simplest way is to put one pi pulse in the middle of the whole thing on the I channel. And this is better in practice than doing equal number of pulses, because if you have a lot of pulses on the observed channel, there's just usually so many pulse imperfections, causing trouble, causing artifacts. Okay, yeah, that's basically how ReDOR works in terms of how it brings back the dipolar coupling. The universal curve that I talked about is the spatial part of it, and that's somewhat separate, but at least I want to explain why a train of pi pulses done this way brings back dipolar coupling. There is some practical limitation. If you're spinning at 100 kilohertz, that really doesn't leave you much time to be putting out 2 pi pulses. So ReDOR was developed by Terry Goulion and Jake Schaefer in 1989. That's when people were spinning at about 5 kilohertz. And it turns out that, we find that at 40, 50 kilohertz, it still works, which kind of surprised me. But it works because finite pulse ReDOR, even when your pulses are occupying 40, 50% of a rotor period, still works. It's fine. It just changes the ReDOR oscillation, pushes it a little slower, but it's still quite nice. Yeah.